Humans have observed many wonders across the cosmos. Yet much of our universe is still shrouded in mystery. Among those mysteries is the formation of our universe, which should have resulted in a balance of matter and its corresponding counterpart, antimatter. Much of that matter is thought to exist in the form of dark matter, which can't be directly observed. Much of the antimatter can't be found at all. Studying fundamental particles originating from sources up to billions of light years away may hold the key to understanding both the composition and history of our universe. Welcome to the world of particle physics, currently being explored from low Earth orbit by the Alpha Magnetic Spectrometer, or AMSO2, installed on the International Space Station, or ISS. Planets, stars, interstellar gas, dust. What we're able to observe across the universe comprises less than 5% of the total content found throughout the universe. The other 95% is dark. Dark matter as well as dark energy. Dark matter doesn't interact with or produce light as far as we know. It doesn't consist of normal matter, or matter that can be observed directly. So how do you improve understanding of something that can't be observed? One way is to look for evidence of its interactions. Kurt Costello, the ISS program chief scientist at Johnson Space Center, explains how the giant magnet of AMSO2 is working to help scientists test and modify their theories. Scientists are using AMSO2 to look at cosmic rays, charged particles that travel near the speed of light. AMSO2 categorizes each cosmic ray, looking at a high energy range to see whether that stellar phenomena that we can measure can account for all of the cosmic rays we're seeing. But if you see something in the spectra that doesn't fit, then this could be evidence of dark matter interactions. By studying cosmic rays, scientists are also able to search for antimatter. The Big Bang theory of the universe's origin requires a 50-50 ratio of matter to antimatter. But to date, the amount of antimatter found doesn't come close to matching the amount of matter known to exist. Costello says one of the goals of the mission is to detect antimatter and see if there are any large collections of it out there somewhere. When particles pass through the strong magnetic field produced by AMSO2, their paths bend. Antimatter particles stand out because their paths bend in the opposite direction compared to matter particles. The instrument searches for antimatter with a sensitivity 3 orders of magnitude greater than the original AMS, which flew in space in June of 1998 aboard the Space Shuttle Discovery. This could support the discovery of antimatter pools that were previously undetectable. A key factor in our ability to get the most out of AMSO2 is time. Originally expected to have a lifespan of 3 years, the instrument has continued to perform into its 8th year of operation aboard the orbiting laboratory. In late 2019 and early 2020, astronauts conducted a series of spacewalks to replace AMSO2's cooling pumps, which were failing. Extending the life of the instrument will provide scientists more time in their quest to unveil some of the universe's greatest mysteries. For more on scientific studies being done on and from the space station, go to www.nasa.gov/ISS-science. For more information about the origins of the universe, visit science.nasa.gov.